Okay, the third form is a new form. It actually uses the idea of the trigonometric form. So the fact that you are defining the complex number in terms of r and theta. In fact, you could also refer to that form as, I'll just go back to this. It's a very good way of, quicker way of naming it. It's polar form as well. Okay, later on in later chapters you will be studying polar coordinates, and you will realize that these two ideas are very closely related. Okay, so the last form, it's called the exponential form. So this form is just a shorthand of writing your trigonometric form or modulus argument form. So instead of writing r cos theta plus I sine theta, you can just replace the cos theta plus I sine theta with what's called Euler's relation. There you go. Okay, so this is Euler's relation. Euler, a very clever mathematician, very famous. He spent his life born in Switzerland, but spent most of his adult life in Russia, in St. Petersburg, and he has contributed to mathematical world tremendously. Anyway, so if you could see that, so we keep r outside, and the bracket can be replaced with ei theta. So it's absolutely brilliant. Okay, now we are ready to move on to example 1, and we're going to finish at example 5, I believe, which will lead to exercise 1a. Throughout the exercise, I think most of the time, unless it will be specified differently, the argument will fall between minus pi and pi. Okay, obviously in some questions it could be 0 to 2 pi, but throughout the textbook this is the standard idea. We're going to go between minus pi and pi, so it's between minus 180 and up to 180 degrees. Okay, so over here you could see that this is in a perfect trigonometric form. There is no minus. You can say that the modulus, which is the value of r, is simply root 2. Argument, which is theta, is pi over 10. So you could write straight away our complex number z is root 2 e to the power of I pi over 10. Okay, I'll very often put an I before the actual value of the angle. It can alternate, but most of the time, actually, I'm not sure. Sometimes they'll do it, whether you put it in front or at the back, it's perfectly fine. There you go, it's done. Okay, example 1b, you've got another complex number. So here you've got straight away the modulus, so the value of r is simply 5, so that is the distance from the origin where the real and imaginary axis cross to the point where the complex number is placed. But here we've got a minus, so it is like a complex conjugate of the same number but with a plus. Okay, so the argument is not going to be pi over 8. So let's just rewrite this complex number with the argument that is negative. Okay, because that would be the argument of the complex conjugate. Okay, so now you could see straight away that this complex number, the argument, so the value of theta, is minus pi over 8. Therefore, in exponential form, we are going to write it as 5 e to the power minus pi over 8 I. Okay, I just realized that I guess you will more often put I at the end if your argument is negative, because that was kind of an automatic thing I've done here. Okay, just as a quick thing, a result you should remember from last year, from Pure, so Pure Maths Year 1, cos is an even function. So if you have cos of minus theta, that will give you the same value of cos theta. If you look at the cos graph really very quickly, just a reminder, there you go. So if you've got a minus theta over here, the value of cos is exactly the same on both sides. However, if you talk about sine, so if you were talking about sine of minus theta, that is going to be the same as negative value of whatever sine theta gives you, because sine theta, if you draw it and remind yourself a quick sine graph, let's just go up from pi over 2 up to pi over 2. Let's say that's minus theta. This here is going to be theta. Let's write it over here. Okay, the value is going to be in opposite signs. Okay, so if I try to work out sine minus theta, I need to find what sine theta is and obviously reflect it, so stick a minus in front of it. So these two identities you need to, you should recall from last year, you need to remember. Okay, so here in example 2, if we come back to the textbook, we've got z is equal to 2 minus 3i. So over here, we have to express it in the exponential, in the form of r e to the power I theta. So we need to have the value of r, which is our modulus. Okay, so it's quickly, you imagine if you just plot that point, you don't need to do it every single time for that particular, if it's an easy question. But really, you just want to consider the distances. Okay, so for that kind of question, whether it's minus or plus, you always square the lengths. Okay, so use a quick Pythagoras. So this is going to be 4 plus 9, so that's square root of 13. Okay, very rarely you need to write it as a decimal. It's better to leave it in the exact form. Theta, which is your argument, okay, this is going to be your arctan, but I'm glad I've drawn it. It's always a good idea, so you could use your simple trigonometry to work out what arctan of 3 over 2 is, but it's going to be minus because we are below the x or real axis, the x-axis. Arctan 3 over 2. Okay, so quickly do it with a calculator. Okay, so this is minus 0.983. Radians, you can put radian symbol or put RAD for rad. This is to 3 significant figures. Okay, moving on, let's go to example 3. So this time we are going to start from our exponential form, and we're going to write it in, okay, so first of all, they're asking us to rewrite it in Cartesian form, so you want to split it into, work out what the real and imaginary parts of this complex number, or numbers. No, for this one, number are. Okay, so we want to go through, recognize that the multiplier here is simply your modulus, okay. The argument is simply whatever I is multiplied by, so it's 3 pi over 4. You can actually imagine that this is going to be 3/4 of pi. Okay, so we are talking about going to the second quadrant, so somewhere over here. This complex number is here. This is its argument. That's root 2. Okay, obviously you don't need to draw it, but it's nice to actually imagine it. So you could work it out from just looking at the diagram. Okay, but we're going to do it how I would recommend it for any other situations. So simply substitute these values into the trigonometric form. So there's your z is equal to r cos theta plus I sine theta. We're going to replace the value of r with root 2 and the value of theta with 3 pi over 4. And just reach for the calculator or work out what cos 3 pi over 4 is. So this cos 3 pi over 4, if I could see that it's going to be negative, but you can reach for the calculator. It's minus root 2 over 2 or minus 1 over root 2. Obviously, if you reach for the calculator, then it will give you minus root 2 over 2. So that's what I'm going to put down, because I imagine this is what you would do. Now this imaginary part, and if you reach for the calculator, this will stay positive. So this is going to be I times root 2 over 2. Okay, multiply out you'll have root 2 over 2 multiplied by root 2. That will give you 2 over 2, which is 1 with a minus, because there's a minus, and this will give you plus I. Okay. The example 4, very similar, except we've got to write it in trigonometric form. So r cos theta plus I sine theta, but this time the argument, obviously, I think I was just wondering why this question would be in there. It's just because you need to be very careful with the argument. Over here, it's perfectly fine for them to sometimes give you a question with an argument that does not fall in between minus pi and pi. So the argument will, imagine just going around a circle, will be the same for every angle that repeats itself every 2 pi. So if this is our argument, so clearly we've done a few more rounds of turning around to get to that angle, but you still would be finding the same value as if you were between minus pi and pi. So all you need to do is to take away or add multiples of 2 pi until you fall between minus pi and pi. So this one here, you could actually see 23 over 5 pi. If you divide it by 5, you're going to get 4 and 3/5 pi. You don't need to do that necessarily straight away, but you can see if I can take 2 lots of multiples of 2 pi. So all I need to do is take 4 pi away from that. So it's 4 and 3/5 pi. I can take away 1 lot of 2 pi, and then I clearly need to take another lot of 2 pi. So it's going to be 3/5 of pi that's left, and that is clearly between minus pi and pi. I mean, if you're using a calculator, if you prefer to do it on the calculator, if you put 23 over 5, so I just put 23 divided by 5, the calculator changes it to a fraction. All I need to do, I don't need to put pi there, but you could if you wanted to. Take away 2, okay, I need to check on that. Oh, it's still too big. It needs to go between minus 1 and 1. So take another 2, okay, check it, that is perfect. 0.6 of pi, 3/5 pi is our required argument. Okay, so the argument is 3 pi over 5. Now modulus is 2. Okay, so that gives us our complex number as 2 cos 3 pi over 5 plus I sine 3 pi over 5. Perfect. Okay, let's move on to the last example. This is example 5. Okay, over here, so what I've jotted down is we are asked to express using this complex number, arrive at this property. Okay, so it actually says use this to show that you get that. Okay, so really what they're asking you to do is just maybe not rearrange, because there's a trick of doing it, but you will have to learn how to do it, because you could have a question like that in your exam. We are going to do the proof. Okay, so this is obviously our Euler's relation. Okay, so the trick of doing this is simply using the idea of solving simultaneous equations. So if you notice over here, we have got e to the power of minus I theta. E to the power of minus I theta is simply e to the power of I minus theta. So this is a complex number that is has the argument of minus theta. So it's these two complex numbers are conjugates of each other. So we really could do with having this written in the Euler's relation. Okay, so if all we need to do is replace theta above with minus theta. Now I'm doing it the long way. You could straight away write it down as cos theta minus I sine theta, because of what I've just said, that these two, so if this is z, then the complex conjugate of that number is e to the power of minus I theta. I would say this is another really important result, something pretty obvious, but when you see it in this form you might forget. So they are conjugates of each other. So actually if you start with this number, then its reflection in the real axis is its complex conjugate, and vice versa. Okay, so what we're going to do is, let me just write these down again. So we are going to put cos theta, one up underneath each other. So we're going to put this one with the minus outside the I. Okay. So if you call that equation 1, and this is I, and this is I, we are going to, we are trying to find what the value of cos theta is. So this is what I was saying earlier. You use idea of eliminating the bit you don't want by the same way you would solve simultaneous equations. So we don't want I sine theta, so they are exactly the same in size but opposite in value. We are going to add both sides. So here we are going to have e to the power I theta plus e to the power of minus I theta equals, add these two together, you're going to get 2 cos theta, and you've eliminated the sine part. So the last thing is to divide by 2, and I'll put cos theta straight away on the left hand side. So you could put a half in bracket e to the power of I theta plus e to the power of minus I theta. There you go. Okay, so now this leads to exercise 1A.